Hello my friends, welcome again to my video channel. Today we will continue and promised finalize our work on the Kenwood TS700S line. There is a light at the end of the long tunnel, and this light is not locomotive which is approaching us with high speed. The famous three lights in the front of the locomotive, it's the end of the tunnel, the real end of the tunnel. There is still some minor work to be done. First thing is to finalize the work on the external Vfo700S. So let's start with the Vfo. Dismantling the Vfo700S is rather easy. We have to remove a lot of screws on the side, bottom, same on the top. Additionally, one screw is here to fix the PCB for the switch. The frame can be taken away. It consists of two parts. There are a lot of screws around the Vfo can be taken out, unplugged of course. This bezel here is held in place by two screws. We can see here. And the third screw is not existing. Here's a flap. Same for this little bezel. Here is a screw. Third one. The other two are here in place. This is the front panel, and we can see it's necessary to clean it. Here where the bezel was, we have the original color, but outside, whatever it is a little bit sticky, dirty. Again, I assume it was a smoker, a heavy smoker. Anyhow, knobs of course are removed. Can be cleaned with lukewarm water, a lot of soap, and wait overnight if necessary to get all cleaned. All knobs, front panels, bezels feed the two frames and the housing are cleaned. The most important work to do is the Vfo inside. There's also capacitor, variable capacitor inside, I assume also with contact problems, as we have seen in the main Vfo of the transceiver, where we have to clean the sliding contact. I assume there's also some dirt, grease in it. I have to open it. After cleaning the contacts on the variable capacitor, here this side, as we did with the TS700S Vfo, I connected it to the power supply, 9 volt, and the scope. We have here the oscillation, and this is the frequency. Hope you can read it. And when I tune it over the whole range, then we see that the amplitude is constant. We do not have any interruptions as we had before, any blackouts. We can tune it smoothly over the whole range. Between 8.0 and 9.0, which is the operating frequency. Well, that's it. So I can reassemble this whole unit. The Vfo shield, the aluminium box, is in place now, and then we have the correct frequencies at 1000. It's the upper end of the 1 MHz band. We have 9.20 something, and when I tune down to 00, then we have exactly 1 MHz less. And this is when we have 0 in the vertical position. We have 8.2000 as it should be. That means the Vfo now is correct. The little difference of some 100 kHz was caused by the missing shield. Okay, frequencies is perfect now, and we can continue. The Vfo is ready. Now it looks much better than before. The Vfo operates perfect now. Only one thing is left, has to be done. This is the illumination of the scale. The two incandescent bulbs are bad. I will replace them by LEDs, by white LEDs. Same procedure as in the transceiver, but in the moment I don't do it. I want to get it electrically operative, and then I will do the fine tuning, the optical fine tuning, and then I will swap the bulbs, and then this should be ready. And of course I do all other necessary checks together with the transceiver during the next alignment procedure. Now to the alignment of the external VFO. The amplitude has to be set to 300 millivolt, same as the main VFO has. The main VFO didn't fully reach 300 millivolt. I have 275 or so, doesn't matter. When I switch to this VFO, you see the amplitude is a little bit increasing. It's a little bit closer to 300 millivolt, 290 millivolt. That's okay. Not more necessary regarding amplitude. And now I will seal this hole here. Same procedure as for the main VFO. A short check of the RIT function, the alignment. It's okay. The VFO is operating when I switch to RIT. There's no frequency jump. Okay, it's always difficult to find the exact center. That's it, the knob has to be centered. We can do another check when the VFO is off. The frequency check when I pull down this knob. The frequency is indicated from the VFO. It is 0. And now this frequency is indicated. It's a short check. That's it. VFO is ready. Step 13. It's the last step in the adjustment procedure. Check of a bandpass filter characteristic. The bandpass filter should be connected on both sides, input and output, this way. And then they are writing here to use a signal generator and to do it step by step for different frequencies and use an feed strength meter or so. I simply use my sweeper. It's easier. It is prepared. Here we have this copper box. This is a bandpass filter. This is the input. I unsoldered it as described in the manual. Connected the sweeper to it. This here is my sweeper. The output from the local oscillator is fed in, and this is the output from the bandpass filter. And this is the input for the detector. And then I can sweep this whole bandpass filter for a special or certain frequency. And it is set to the 2 meter band. And we see a perfect characteristic. This is 144 to 146 megahertz. And here we have the center, 145, and the attenuation is 0.57 dB, minus 0.57, and it should be better than minus 0.7 dB, what it is. So we have here a perfect characteristic. And for frequencies, plus minus 10 megahertz, from the center of the frequency, the attenuation should be better than 11 dB. I will set the markers. The measurement of the specified bandwidth. It is more than 11 dB, minus 11 dB, at plus minus 10 megahertz. So we have the center frequency. Minus 10 megahertz is 135, and plus 10 megahertz is 155. It should be more than 11 dB. This is a minus 11 dB line. And we have here a little bit more than 40 dB. On this side, here a little bit less. So the specification is fulfilled. And the filter is okay. And now checking the noise blanker. The idea is to use a pulse generator. It is specified only up to 50 megahertz. Also the rise time, which is minimum ramp time, minimum 6 nanoseconds, is a limitation of 50 megahertz or so, but there are always some harmonics up into the 150 megahertz range. And indeed, I have here an output. This is the antenna of the output, and here I have the antenna of the input from the TS700, and we can hear the signal, the duck duck duck, with this repetition rate. I can increase or decrease the sound, and when I switch on the noise blanker, the noise disappears. And now I will do the same when I feed in a weak signal to see what happens when we have a signal plus noise, plus the ignition noise, what happens, whether the signal is still audible or not. And now we have a signal from the signal generator, 145 megahertz, transmitted with this antenna, some millivolt in the output. Still our combination here, and now we have the signal plus noise. When I switch on the noise blanker, the noise nearly disappears. Back again, so obviously the noise blanker works. This is mode USB, upper sideband. Now checking the output power. Mode is FM. The watt meter is connected to the output. We have here totally an attenuation of 30 dB, and the head is connected. We set the sensor to 0 milliwatt here is watt here, so we have totally 30 dB. And in FM I'm 144 high power. We have an output of approximately 13.9, means 14 watt. We can peak it with the driver a little bit. That's it. When we go to low power, we have output power of 3 watt. That's okay. Then let's go to 145, 1 megahertz up. Oh, let's check it here. The center of this range. $14 watt, it's okay. And now we're at 145. $14 watt. In low position we have 3 watt. Now 1 megahertz up, 146. Peaking is a little bit effective, it's okay. 13 watts. Low power 2.2. That's it. Output power is okay. It is as specified. And now, just for curiosity, some checks in the mode USB and AM. First USB. I'm generating here a 2-tone signal from this generator. Here's a simple pot. That's the input, microphone input. I can adjust the level. The Vox is on. When I increase the input, then the Vox is activated. The output signal is damped by 30 dB into the spectrum analyzer. Top line is 20 dBm plus 30 dB. It's 50 dBm, that's 100 watt. And 1 critical down is 10 watt. That's the nominal power of this transceiver. And now I increase the output. I have a frequency, 2 frequencies, audio frequencies, 700 Hz and 1700 Hz. So both ends of the speech range. And when I increase the input, signal is triggered. We wait for the whole sweep. We do single sweep. Okay, and I can reduce the output power and we can have a look at the screen. We have here the two tones. This is 10 watt and 2 or 3 dB down. So I would say 5 watts per peak, so totally 10 watt. And the difference here to the unwanted signals is only 20 dB. So when using high power, this transceiver is not the best one. It's a problem of the linearity of the PA. In general, it's the PA transistor which is bad. I can repeat this measurement with lower outputs. One moment. We have one complete single sweep. It ran away, it drifted a little bit, it is not locked. But now the difference is we have 1 watt per peak. 10 watt, 1 watt, and the distance now is 10, 20, 30 dB. So the signal gets of course better when the output is lower. Again, it's in general the bad transistor. In those days the transistors were more or less designed for class C operation and not for true linearity. That's bad, but it is as it is, and you can imagine when you use a PA behind what you are doing on the band, and the neighboring stations will be very happy, and you can also make a QSO with them without being on frequency. Now let's check the AM mode. We have the unmodulated carrier now. It should be, according to the manual, a quarter of the maximum power of the FM mode. So this would be approximately 3 watt. This is 3 watt. We have here 10 watt, 1 watt. This is 3 watt about. And then I increase the modulation. 2 tones. Okay. We have a typical AM signal. While the amplitude is different, but we have the carrier. I will do a single shot, one moment. We have the carrier and the 2 tones, 700 and 1700, 700 and 1700. We have both sidebands in the AM, of course. And when I increase the total sum, what's going on? What did I wrong? Why is the amplitude so different? I have to check the setting of the audio generator. No big difference. I increased the frequency from 700 to 1000 Hertz, but we have still here an increasing output with higher audio frequencies. Well, the power of the sidebands should be approximately each 25%. We have 50% in the AM signal, 50% power in the carrier, 25% in the upper sideband and 25% in the lower sideband. So I can increase a little bit the power, okay, still a little bit more. Single shot, and we can see the signal is rather good. We have 10, 20, 30 dB suppression of the unwanted signals. That's rather good for the simple AM circuit, but same as in SSB, we shouldn't use a PA behind. Well, that's it. The rough check is made. It's not a precise measurement. We would do a much better procedure. It's only to get an imagination what the output is. This is a setup for the measurement of the receiver sensitivity. We have here the receiver, the output, the speaker output is connected to the scope. Here we have the termination. According to the speaker impedance, it's 5 ohms or so. The true RMS voltmeter is connected in parallel, and the signal generator is connected to the antenna input. In the moment we have no signal input, So we have a level of minus 10 dB, and for 10 dB signal plus noise to noise we need 0.25 microvolt in SSB and CW. We are working on 145, it's set to 144.998785, okay. We will tune it for maximum when we have an input signal, and I will increase the input of the signal generator. I do not touch the AF pot here until this pointer goes up to 0, then we have 10 dB more with signal plus noise. This is noise only. The scope is only there to see whether we have any clipping or so. But I checked if there is no clipping. Now I will connect the HF, the signal generator. Now we have 0, I tune it for maximum. You also with this drive pot can I reduce it a little bit. And without signal, just for comparison, it goes down to minus 10, that's okay. It's not important for absolute precision. And when I go to the analyzer, I'm measuring a signal of 0.21 microvolt. We should have 0.25 microvolt. So the 0.21 is a little bit better than expected. The preamp is not on. You can see it here, preamp is switched off. I noted 0.21 microvolt, and now same measurement with the preamp on. You see we have an increase in the noise. I reduce the output of the speaker, and then I look for the necessary input signal. I connect the generator. Same signal as before. Okay, it's a little bit too maybe I will increase this measurement, and then we have a little bit more, 0.5 dB more. I can reduce the signal to 0.20 microvolt with preamp. One moment. Okay. Yes, 0.20. These are the two figures, 0.21 microvolt without, and this is with preamp, so the sensitivity does not considerably increase. We have more output, but more output does not mean a better signal to noise ratio. More output only means more signal and more noise. So this preamp here is more or less okay. I would say it is useless. And now the measurement in FM. There's a threshold of 0.4 microvolt for 20 dB noise quieting. I have here noise, no input signal. It is set to 0. And I have to increase the signal. I connect the generator now. And go 10 dB down. And I have to meet minus 10. And I'm measuring a signal of 0.25 microvolt. should be 0.4. Okay, I'm a little bit better. When we take out the signal and 10 dB up, okay, then we are here again. It is indeed 20 dB down with this signal. 0.25 microvolt for FM, yes, that's okay. Well, the receiver of the sensitivity of the receiver seems to be within the specified range. It is not bad, it's acceptable. The last step of the reassembling of the transceiver is the repair, or was the repair of the handle. You remember, it was totally kaputt. The Twan was broken. I took a needle. Took me about 2 hours to insert the new Twan, black one, and now it looks like new and it can be reinstalled. Doesn't it look great? In the check, PTO or VFO, smooth and silky, cleaned, aligned, everything is okay. I only have to readjust the crystals, which are not perfect. They are all 500 Hz too low. This is the consequence of the new alignment of the heterodyne oscillator, so I have to realign them, but it's another topic. Yes, but this line is a little bit space consuming. Today you can get transceivers half the size of this one, like this also, with many VFOs in it, and the frequency range from all shortwave ranges, VHF, UHF, not only VHF like this. This is only a VHF equipment, but it has, compared to the radios transceivers today, some advantages, and we will discuss it now. I found an interesting website from a German old man, Delta Fox 9 India Charlie. He started in 2005 a test of a large signal behavior of some 144 MHz radios. I will show you the link in the description of the video. You can download it. It is written in English language. No fear, it's not German, it's in English. There are old and new transceivers compared. This is a row for the TS700S regarding noise figure IP3. The IP3 is not so important for VHF receivers because there are not so many strong stations on the band. There is some other value which is important. That's the sideband noise of the transmitter and the RX blocking mode for different offset frequencies. The RX blocking for different offset frequencies is caused by the noise of the oscillator, of the local oscillator. And the TS700S, for example, has a value of 100 for 20 kHz offset of 100 dB between a minimum discernible signal and blocking effect. And this 100 dB is not bad. There are only some radios which are a little bit better. TS790, a homemade one. But some of the newer ones, IC, FT, TS and so on, are not so good. The reason is that some of these modern radios have a poor LO design. The local oscillator is more or less a noise generator. And also the TX sideband noise, here it is suppressed by 20 kHz, offset by 96 dB. Others only have only 80 dB, 96. This is a homemade one, minus 100. IC202. The IC202 is a very good transceiver, but it has not a synthesizer, it is a crystal oscillator, and therefore it has a very, very clean signal. Have a look at this table, it's very interesting for those who are interested. The ARL, American Radio Relay League, also made such tests. I don't know whether they are available for the for all users in the net or only for the members of the ARL. I don't know whether there is a barrier or not. Anyhow, it shows that such a transceiver has advantages in the region of noise, sideband noise, and it is for true experts an interesting transceiver. It has of course no possibility to control the operation frequency and automatically generate the QSO list and so on. But for specialists which are looking for very quiet receivers, these old types are not the worst selection. And now to the end, a short discussion of the question, was it really worth to swap all electrolytic caps? My clear answer is no. There was only one capacitor, I think this one, who had a bad rubber, and where there's one spot where the electrolyte dried out and came through. And the other one, similar one type, had a little bit of loss of capacity. But all other electrolytics I checked. I only made, of course, a random check every second or third. They were all good. Some had a little bit high increased ESR in the range of 2 or 3 ohms. But many applications of these electrolytics are not affected with an ESR of some ohms, because when these are coupling capacitors between 2 AF stages, an ESR of 3 ohm is not critical. Or when they are blocking capacitors in the emitter resistance of an amplifier and there's 2 or 3 ohms in series, it reduces the gain a little bit, not more. The isolation was always good in the range of dozens of meg ohms. Some reached 100 meg ohms, and when I compared it to the new ones, they were not worse than the new ones. Of course, this transceiver rested very long time in a garage or so, and maybe when it is operating now for several hours, some of these electrolytics may start to go away, to go home and say, I don't want to work any longer. So this swapping all electrolytics was maybe a good idea, but in the first step I don't think it was necessary. Anyhow, I did it. Took a lot of time. And now we are, can't believe, at the end of this project. It took a lot of time, as you have seen. I roughly estimated the total time of work for this TS700S line, 40 hours or 50 hours, I'm not sure. It's difficult to calculate because I did some paperwork when I was not in my workbench, on my workbench here, when I was sitting in my living room, drinking some wine or beer and thinking about this project, doing the paperwork. I didn't count the hours, but the swapping of the electrolytics, when I calculate 3 or 4 minutes per electrolytic, it's not only take the old one out, the new one in, it has to be compared with the parts list. The orientation has to be checked with the layout, with the schematic and so on. So this took 300, 400 minutes, which are 5 or 6 hours, the generating of the list. To buy the electrolytics at the distributor, also 3-4 hours totally, cleaning and all the other work, aligning, repairing, checking again and so on. I think totally 40 hours is not too much for this work. Another question, is it worth to do such a work? It depends. Economically, no. When you calculate a working hour of a skilled electronic engineer, 80, 90 euros per hour. My gardener, who is digging holes in the ground, takes, I think, 50 or 60 euros per hour, including everything. So I think a skilled electronic engineer, including all the equipment, is not overpaid with 90 euros. take it times 40, times 50, then we have 3,000 or 4,000 euros. With this money you can buy the best transceiver now in our days. But it gave me a lot of fun. It was interesting, I've learned something. I hope you also learned something. And I think it would be a pity when such transceivers or lines disappear in a trash can or so, are thrown away. I think that they deserve a second life. And this is my goal here, to give them a second life. And I also have some personal reminiscences. When I was a young amateur decades ago, I wanted this line, I couldn't buy it, I had no money. So I thought now it's the time for me to make such a project, to have my hands on this line. That's it. Thanks for watching. Hope you have enjoyed it. Stay healthy, stay tuned. See you on this channel.